Okay. Cool. So last time we introduced magnetic fields and the Lorentz force, which is the magnetic force on a moving charge. Right. So we have Q V cross B. And then at the very end, we said that, oh, well, if you have a bunch of moving charge, that's just the current. And so there should logically be magnetic forces on currents. So we'll talk a little bit more about that today. And then we will start talking about magnetic fields produced by currents. All right. So, so for moving charges, we had point charges basically. We had this. And so now, instead of dealing with a moving point charge, what we're going to deal with is instead a small bit of wire. It's carrying a current I. It has a length dl. The direction of dl is the direction of the current. And it's placed in some external B field. So small current segment is external B field. And so it's a small length of wire, so it's going to be a small force, and that small force is given by dF is equal to I times dL. And basically, if you have a longer bit of wire, you just end up integrating along that wire and adding up all the force vectors, and you get total force. So often we'll deal with straight line segments, and so then it will reduce to for straight wire. You can just, they all end up pointing in the same direction. So it ends up being just this. But you could treat like weird curly loops and whatnot. I think you saw some of that in the checkpoints and the prevention. Question? Yes.
Where are you integrating with respect to?
Here you would integrate along the length of the line. Other question? Okay. Let's actually jump into a couple of quick questions. So go ahead and get your paper clippers out. Start with this one. We'll start with one last point charge proton magnetic field question, and then we'll move on to the current carrying wires. All right, fairly unanimous for A. Let's see, Angelica? Wanna give it a shot?
I think Will would be better at.
Just give it a shot. Just give it a shot. Sure. No pressure.
So B is.
B is perpendicular to B. Yes.
And so.
No, that's a crucial point. Yes.
Yeah.
So there's not going to be any helixing because there's no component pushing it that's not perpendicular.
So the last time when we had a helix because we had to split the velocity into a component which was parallel to the B field and a component which was perpendicular, right? And the linear, sort of the steady motion of the helix is due to the part which is parallel to the B field. And here there is no such part, it's all perpendicular. So yeah, it's just going to be a circle.
And
The force is in the xy plane. Exactly, that's another good way of putting it. The force is in the xy plane, the velocity is in the xy plane, it just stays in the xy plane. Questions? Okay. Let's try. Let's try. Yeah, okay, quick one. And E is correct, no force. So in this case, the direction of the current, which is the direction of L, is exactly opposite to the direction of B. So when you do the cross product, you get here. Yep. All right. And what about this? So here the B field is only inside the green square. Okay, all right, so people narrow down by the C or D. So let's just check. So there are two bits of the wire inside the magnetic field that will feel force. So this segment of wire, so I would do IL cross B, the force would be in the positive X direction. And this bit of wire, I would do IL cross B, right, coming out of the page. Force would be in the negative X direction. And which one feels a stronger force? This one feels a stronger force because the field lines are closer. And so the force will also be stronger. Questions? Yes.
What if the field was at like an angle of some sort, if it wasn't directly in line with the y-axis?
If it was at an angle, basically you would have to do this product, this cross product for each segment. And we know that like if you just need the magnitude, we know that the magnitude of this would be ILB sine theta, where theta is the angle between the direction of the current and the direction of the B. All right. Okay, so we've been talking about the force experienced by currents placed in the magnetic field. But not only do currents experience forces from magnetic fields, they produce magnetic fields. And so here we're going to introduce, in this section on magnetism, we're going to look at a lot of right-hand rules, unfortunately. So it's a good idea to start like making a list. Most of the time it comes down to just like, oh, you're trying to do a cross product and you're using the right-hand rule associated with that. However, this one is, you can trace it back to that, but it's a little bit quicker if you just use it as a sort of new right-hand rule. I'll just tell you the answer here. If you have a current, so in this case, the current is coming out of the page, you have magnetic field lines that are going to be circles around it. They don't start at the wire, they just loop around the wire. And so then it's like, oh, do they loop clockwise or counterclockwise? And so the rule is you put your thumb in the direction of the current, and your fingers will show you which way, the right hand thumb in the direction of the current, and your fingers will show you which way around the wire the field lines will run. So in this case, I see that, okay, looking from this point of view, they are wrapping counterclockwise. So the field lines would look something like this. So a couple of interesting points here. One, again, this is a somewhat intentional diagram. So you can see, okay, yeah, the field lines are closer together near the wire. The field is stronger near the wire. Makes sense. Gets weaker as you go further away. Right now, we're just going to treat that qualitatively, and we'll look at it quantitatively a little bit later. The other thing is that it's interesting. Here with magnetic field. Oh, question.
I was just gonna ask, like, why does this happen? Is this just like a law?
This is pretty much just a law. Yeah. Currents create magnetic fields. And what's interesting is that, you know, they're sort of sourceless. Well, they're not sourceless in terms of it's the current that's causing the magnetic field, but they don't start on a charge, right? They just loop around into themselves. All magnetic field lines are like that, basically. At most, they can go off to infinity or come from infinity, but basically, anything that stays in a finite region, it's going to loop in some manner. All right, so let's keep this in mind. And one of the most common confusions as we move further into magnetism, one of the most common confusions is getting confused between, oh, is this some external B field that a current is placed in, or are we talking about the B field produced by the current? So always read the questions carefully to see what the question is talking about. Is it the current being placed in some external B field, and we're ignoring the field produced by the current, or are we actually looking at the field produced by the current? Question? Okay, let's try this then. Oh, question.
If we were to put a wire that had this unit,
Uh-huh.
like a third wire,
Oh, I see. Okay, so I think what Aiden is asking, if I can draw it. So right now we have, say this is the current. In fact, we get some color so we don't get confused. Let's say that I'll use orange for the field produced by this current. So it's going to wrap around. Should be getting further away, but yeah, like that. And so you're saying if we put it in an external field, which is going like this, that's interesting. Basically, if it was exactly concentric, that would mean that that field is being produced by a current that is running along the same wire. So it's sort of neutralize it. If it was lying exactly on the same line.
I think a good example is the fact that a lot of wires are like run next to each other, like a coax cable.
Right. Okay. Yes. So if you have a coax cable, so coax cable, you have basically central core like this, and then you will have the current often returns on an external sheet like this. So here what I'm indicating is this current is coming out of the page here, and this current is going into the page over here. So let's see, in this scenario, Okay, yes. We'll have to look at the details. If it was a perfectly uniform shell of current flowing like this, it turns out that you would not have a magnetic field inside. It's we're going to see a little in a probably actually yes. Ampere's law, which is sort of like the magnetic equivalent of a magnetic analog of Gauss's law, where in Gauss's law, if you had a uniform shell of charge, there was no field inside. Similarly, if you have like a cylindrical shell of current flowing like that inside the hollow space, there would be no field due to the shell. There would be a field due to this current here in the center, but not one due to the shell. Cyrus and Kyle.
But unrelated question, that's related, like, first one, like, what happens if you just have one battery that's 10 volts this way and another one that's 10 volts this way? Is that a short circuit? Would it just drain both the batteries?
Oh, well, if they were, okay, so Cyrus's question, let's throw in a resistor. Turn that off. But let's say this was E1, this was E2. If E1 and E2 were equal, then they cancel out and there'd be no current flowing. If one of them was bigger than the other, then that would drive current through. So like say E2 was bigger than E1, it would drive current this way. It would be reduced current, but it would be basically charging actually. Oh, when you say behave like a capacitor, what do you mean?
Yes, two G's of charge.
Oh, I see. There are capacitive effects in long wires. Yes, no, that is definitely something that they look at in electrical engineering. But you have to remember that in most current carrying wires, what's actually going on? You have these fixed protons, and then you have electrons that are moving. So it's electrically neutral, right? There's equal amounts of positive and negative charge, but one set of charges is moving. Right? So you can get a magnetic field and like negligible electric field because you have equal amounts of positive and negative charge. Is that? Yeah. Okay. Other question? Okay, so yeah, let's return to this question on the screen. So here we have two wires. In this case, currents are both going up. In this case, one going up, one going down. And I'm asking you to compare the B field at the center point. And here we're talking about the B field produced by the wires. Okay, mostly from B. B is correct. So we can see it over here. So if I look at the magnetic field due to this wire, you can see that, oh, okay. Remember, it wraps around in circles around the wire. So that means at some point it's going into the screen, at some point it's coming out of the screen. So you can see, oh, on the left of this wire, it comes out, on the right, it goes in. And similarly over here, on the left of this wire, it comes out, on the right, it goes in. Right? It's looping like that. And so you can see that, oh, they're pointing opposite directions here at the center. So they will cancel out. Whereas here, you can see that in both wires are producing a field into the page over here. So they would add up. Okay, so we did all that. Okay, yes, so I've mentioned this. Oh, I guess before I move on, let me do a quick demo. Yeah, sure. You've already seen this one last time. You sort of presented side on. How's the view?
I think I got it, but now it's moving. Okay.
Good. Okay. Let's see. Right. So you can see, and if I stop it bouncing around, you can see it's now hanging at an angle, right? And so we can figure out which way the current is flowing, because the force has to be like this, and we know that the B field is downward. So let's see. To get my thumb pointing this way. Yes. So the current is coming in this segment, is coming towards you, right? And so I have current, B field, force, like that. Question? Sorry, say again?
Is it?
Open? Yeah, it's at an angle. Yeah. I shouldn't run the current for too long. And then if I, oops, if I put the switch the other way, it should, yeah, swing the other way. So now the current is coming towards me, and so I would do current towards me, field downward, force this way. All right. Just another illustration of the same thing is that is that demo over there. So I'll just the jumping wire demo. But basically, yeah, you just have a wire and we're going to run a current through it, and this is a nice strong horseshoe magnet. Wait, hold on. Why didn't it jump? Oh, it's trapped. Okay. There we go. Okay. So a loop of current acts like a magnetic dipole. So let's see that in a bit more detail. On this board. So let's say I have a loop of current like this. So even though it's not a straight line, we can like take small segments and figure out what direction the B field produced by this current is, right? And so you can see that, oh, okay, over here, it would produce a field going into the board over here, and out of the board over here. So let me. So field coming out of the board over here, into the board over here, and the same would be true as we go around. So it's everywhere inside coming out, and outside the loop it is going in. So right now you might say, well, that doesn't quite look like a dipole. Why do we say it's a dipole? So let me take this and rotate it. Okay, so say that I'm looking, supposing it's like just two loops of a wire. Okay, and I'm looking at it, it's flat like this now. All right, and let me blow this up a little bit further actually. Right. So the idea here is that this is the loop viewed from the side and sort of cut it in half so that you can see like a semicircle. right? And so, let's say the current is coming out over here, and current is going in over here, so it's going like that. Yes?
Are the endpoints, is that representing current?
Yeah, so the idea here is that like I've taken. Do I have? Why did I? Oh, actually, I forgot I have a loop. Yeah, all right. Taken a loop, turned it like this, and then I'm looking at like what's happening with the currents at like these points. Like, is the current heading towards me or is the current heading away from me? Right, so the circles at the end sort of represent the cross section of the wire. Everyone got the mental picture? Yeah. Okay. So what do we know? We know that the field lines will wrap around these wires. So what we would see for the field lines would be like that. And then over here, like that. Right, and you can see that, oh yeah, the currents would, the fields would add up and become stronger over here. They'd be a bit weaker outside. So you have a situation like this. And now you can imagine doing this for like several loops of wire tightly packed. And so then we end up with something called a solenoid. Solenoid is basically like a solenoid is basically just a spring structure. So it's like this. And so let's say you pass the current through in the appropriate direction. What you're going to end up with is nice uniform field in the center, and then out here it loops around like this. Questions here and then there, yes.
So what makes this a dipole? I mean, yes, it has a strong magnetic field, but how do you know which end is the north and which end is the south?
Okay. So if we treat this as sort of a black box, if we don't look at what's happening inside, what do we see? We see that, oh, there's this long object, and the field lines are coming out over here. So this is the north, and they're coming in over here. So this is the south. Angelica?
On the top example.
Yes.
I'm just kind of confused with why the ones get stronger. It's like, aren't they like all around the entire of the wire? So wouldn't it be like?
Oh yes, but the idea is like this set is producing many field lines, right? This set is also producing many field lines, and here in the center they both agree in which direction they're pointing. Whereas if you look over here, this set of wire is producing a field downward. This set of wire is producing a field here, which is upward. So they slightly weaken each other.
So are those middle field lines like inside the ring?
Yes.
Oh, okay, that makes a lot.
Okay. Yes. Yeah. These represent these ones.
Okay.
So if that is the black box, so that is that equivalent to a bar magnet?
Yes, this would be equivalent to a bar magnet.
But for this one, it has to be current inside the loop. So for bar magnets, I wonder what creates that kind of magnetic force.
It's basically on the atomic level, it's either the orbital or the spin motion of electrons that creates that.
It will keep doing this motion.
Yes. Yep.
And this is
Question.
Can you say again what this is called?
Sorry.
That's-
Sorry, say again. Sure, this is a solenoid. Yeah, sorry, that's not intuitive how to spell that, yeah. Other questions? Okay, so we see that every current loop is a dipole, right? That's like this, and just like we had a dipole moment in electric dipoles, we can have a dipole moment here, and that would point like this from south to north. But here it becomes sort of clearer why they chose this direction for the dipole, because you can see that, oh yeah, the field lines come out over here, they go in over here. It sort of makes sense. And now all the results that we have for electric dipoles, we have again for magnetic dipoles. So the usual symbol for, well, not usual, there are a couple of different symbols people use for magnetic dipoles. It's either mu vector or it's a little m vector. I'm going to use mu, but yeah, I've seen both be used. So this is the dipole moment. So if you place a dipole in an external field, what did we talk about when when we were dealing with electric dipoles? We talked about the potential energy of the dipole in an external field and the torque of a dipole in an external field. So this is for dipole in an external field. And so just like how for the electric case we had U is equal to minus P dot E. Now over here we'll have U is equal to minus mu dot E. And just like we had torque was P cross E. Similarly over here we'll have torque is mu cross B. Yes, it's right. What is B again? It's been a while, yes, yeah, no, this was like back in the book. That is the electric dipole moment. Yeah. We haven't used it since like, the second week of class or something, so I don't blame you for forgetting it. Yeah, so this one is the magnetic dipole moment. I'm using mu, but for the electric one, we use Other questions? Yes.
So is the work the magnitude of
I mean, the usual relations apply. Yeah, the work done by the B field will be negative delta U. Yes.
so does that mean the work equal to work? Oh, it's cross.
Yeah, one is a cross product, one is a dot product. Yeah. Okay, so let's do one quick question and then a demo. Okay, I'll come back to that. Good. Talk about that. So this is just showing that if you have a loop of wire, you can treat it like a bar magnet. And there is again another right-hand rule. Oh, question. Sorry, I'll do the question first then. Yeah. Good question. Yeah. So for you might remember that for the electric dipole, we had P is equal to Q times D, right? It was how much charge, and like you had a plus Q minus Q that's separated by a distance D. For mu, it's quite interesting. It is NIA. Okay, so N is number of turns. So this would be an N of 2, right? 2 turns, 2 loops, right? I is the current. And A is the area of the loop. And you can see that it's an area vector, and yep, it's perpendicular to the area of the loop. Yes.
What if the current changes within the loop?
Ah, I see. Okay, so you basically have, well, if it's a single bit of wire, it won't, because it'll be all in series. If you have multiple bits of wire, then you'd have to treat it like a superposition of several dipoles. Yes.
Which direction do we choose for the area vector?
Good question. So yeah, so this is the sort of there's one more right-hand rule. So we said that the dipole moment is inside the dipole. Sorry, we said inside the dipole it goes from south to north like this, right? So what we notice is that that is the same direction as the field in the center of the loop. Right, so if you know the direction of the field in the center, that is the direction of the dipole moment. So this would be the direction. So in this case, it would be coming out of the board. There is a quick shorthand way of finding the direction, which is if you have current flowing in a loop, this is a new right-hand rule. Curl your fingers in the direction of the current, thumb gives you the direction of the dipole. Okay, so you can see like this over here, or in this scenario, you can see current coming out over here, going in over here. So yes, the dipole is pointing out. All right, I'll save the question for next time. I'll do the demo and probably bring the demo back next time also. So what we have here, just a bucket of water. This is just a iron rod or steel rod. And yes, I have a loop of wire. I'm going to put a battery in so that there'll be current flowing in the loop, and it'll become an electromagnet. It'll become a current carrying loop, and so it's going to act like a dipole. So just float it here. All right, so it's acting as a dipole. And then the idea is I'm going to magnetize this rod by putting a strong horseshoe magnet over here. And you could see it started turning and reacting to it. And in fact, it's been attracted. And yeah. And now if I take the horseshoe magnet off and then flip it, you can see it's repelled. Wait, rotates. And then should. Yeah, it's coming. Yeah, there we go. And attract it back up. All right, so we'll talk about this in more detail next time. But yeah. All right. Don't forget, there will be a quiz this week on Kirchhoff laws and resistance.